right, so we have been working with exponentials, and our warm-up for today is going to be to take the derivative of e to the x, e to the e, x to the e, and x to the x. So pause your video, try those 4 problems, and unpause when you're ready to check. Pause now. All right, so we have our different combinations. Here we have a number raised to a variable, and the derivative of that exponential is just e to the x. Here we have a number raised to another number, so a number to a number is a constant. That derivative then will be 0. Here we have a variable raised to a constant. This is a power rule. We're going to swing the e down and then lower the power by 1. Here we have a variable raised to another variable, so we're going to need to introduce logarithmic differentiation. So I temporarily call this y, take a natural log of both sides, and then here is when I actually did some calculus, isolating my dy dx. So this final answer is 1 plus the natural log of x times x to the x. All right, a couple more warm-ups. Find the derivative with respect to x of each. So we're assuming here that u is a function of x. Go ahead and see if you can apply your rules for taking the derivatives when the base is not e. Pause your video, try these 2. All right, so a couple of reminders of taking derivatives of exponentials. The derivative of 2 to the u is going to be itself, 2 to the u, times the derivative of the exponent times the natural log of the base. Then for logarithms, log base 2 of u, the derivative is 1 over the argument times the derivative of the argument times 1 over the natural log of the base. So this was kind of an expansion of our understanding of derivatives with base e. Today then, we are going to work to say, well, if we know that the derivative with respect to x of b to the u is b to the u times, oh, my pen is doing weird things, b to the u times du dx times the natural log of the base. Think for a second, it says to work with your groups if we were in class. If you're not in class, then think for yourself and see if you can come up with a formula for the antiderivative of b to the u. I'll remind you that the antiderivative of e to the u du was equal to e to the u plus c. So think about how things might need to change or adjust based on our derivative rule up here in order to get the integral rule down here. Take a minute and just kind of think. Work through it. Make a guess. It's okay to be wrong. See what your intuition comes up with. Pause your video. When you're done, unpause and we'll talk about it. All right, so some things to think about is that if I try to just apply this e rule and say that the antiderivative of b to the u is equal to b to the u plus c, I should be able to check my answer by taking the derivative. And when I take the derivative here, I get b to the u times u prime times the natural log of b, and then the derivative of c is just 0. Well, this is good because I get b to the u and du, right? That du is the infinitesimal. It represents the variable of integration. Here we've got some implicit with the dx. Regardless, though, I get b to the u times the derivative of u. I don't have this in my original function, which means that maybe from the very beginning, I should have adjusted by 1 over the natural log of the base. So let's get this written down, and then I'm going to show you the workaround for how and why this happens. So our official formula is going to be 1 over the natural log of the base times b to the u plus c. And this formula only works if the variable in the exponent is a perfect match to the variable of integration. Okay, so those expressions are identical. Let's talk, though, about why this works, because that's my job as a teacher, right? I'm going to talk about this from the perspective, we'll go with x's, because I feel like people are more comfortable with that, the integral of 5 to the x dx. And if I want to be creative in my math, this would be the same thing as e to the natural log of 5 to the x dx. Right, because e and natural log are inverses of each other, so those would cancel out. We're back to where we started. So if you're like, well, Ms. Schwartz, why would you do that? I can swing the x down in front. X times the natural log, that's a natural log, of 5 dx. Oh, whoa. Now, I don't have this exponent thing, I just have an e, and I know how to work with e. I'm going to let u be equal to the natural log of 5 times x. Du then is the natural log of 5 times dx, because natural log of 5 is just a constant. So if I go through and I do this substitution, I'm going to end up with e to the u times my dx here, dx, gets replaced with 1 over the natural log of 5 du. Now, 1 over the natural log of 5 e to the u plus c is my final answer. The only thing is I need to go back and replace my u value. My u right here was supposed to be natural log of 5 times x. So I'm going to have 1 over the natural log of 5 times e to the natural log of 5 times x. And I can go back and redo with this what I did with this. This whole thing is the same thing as just 5 to the x. And if you're watching that like Ms. Schwartz, it seems like a lot of work. What? Why? What are you doing? This is the formula that you need to have coming out of there, okay? But I had to show you how it works, where it comes from. It's based on what we know about the natural base, which is so important in calculus. So let's try some examples together. Check by taking the antiderivative. First of all, I can take a 6 out of here because 6 is a constant. So 6 integral of 4 to the x dx. This right here matches my rule because x and dx are a perfect match. So the 6 is chilling. This will be 1 over the natural log of the base times itself, all plus c. Now, how do we check our answers? Well, I can check my answer by taking the derivative. 6 over the natural log of 4 is just a constant. It's going to hang out. The derivative of 4 to the x is 4 to the x times 1 times the natural log of 4 from our rules from before. These then cancel, and I'm left with 6 times 4 to the x, which is exactly what I had in my integral. Next one, 8 to the 7x. Well, I can't take anything out in front because I don't have a constant multiple. My 7x is not a perfect match with my variable of integration, so that should be an indication that I need a u sub. So when I go through and sub this in, I'm going to get 1/7 the integral of 8 to the u du. Now this matches my formula that I just derived for everybody. The antiderivative of 8 to the u will be 1 over the natural log of 8 times 8 to the u plus c. Last step then is to replace your u with a 7x. How do we check our work? We take the antiderivative. So 1/7 is chilling, 1 over the natural log of 8 is chilling. The derivative of 8 to the 7x is 8 to the 7x times the derivative of the exponent times the natural log of the base. The derivative of c, just like over here, becomes 0. Well, look what cancels. 7, natural log of 8, natural log of 8. And I'm left with my original expression in the integral. Couple more. I've got the integral of cosine times 9 to the sine x dx. Looking at this, I have a product. We do not have a product rule for integrals, so in my head I should be saying I should try a u sub. My expression in the exponent is not a perfect match to my variable of integration, so that's what I'm going to go with for u. U is equal to sine of x. Du then is equal to cosine of x. Oh, look how nicely this is going to work out. So when I go through and I do my substitution, cosine of x dx gets exchanged for a single du. And then 9 to the sine x becomes 9 to the u. This then is my brand new rule. The antiderivative of 9 to the u is 1 over the natural log of 9 times 9 to the u plus c. Check my answer, take a derivative. 1 over the natural log of 9 is just chilling. The derivative of 9 to the u is 9 to the u. Oh, shoot. I forgot to go back and plug in my u. Stop me. Oh, wait, you can't stop me. I'm in a video. Just kidding. Wait. Hopefully you caught that. Yikes. My u was sine x. Okay, let's do that again. 1 over natural log of 9, just chilling. This becomes 9 to the sine x times the derivative of sine x times the natural log of the base. Derivative of c is still 0. cancels, and I'm left with somewhere up here. There it is, what I had in my original integral. All right, number 4. Only difference here is that I have two terms separated by subtraction. So when I get started, I'm going to split that up. I'm going to have the integral from 0 to 1 of 5 to the x dx minus the integral from 0 to 1 of 3 to the x dx. Look at this variable expression matches my variable of integration. So this is just going to be 1 over the natural log of 5 times 5 to the x. I don't need a plus c. I need evaluate between 0 and 1. Come back to that in a second. Next one, x matches x. So this one will be 1 over the natural log of 3 times 3 to the x, evaluating between 0 and 1. Fundamental theorem says I set in this top bound first. So I'm going to have 1 over the natural log of 5 times 5 to the first minus 1 over the natural log of 5 times 5 to the 0. Then I'm going to subtract, carefully with parentheses, 1 over natural log of 3 times 3 to the first minus 1 over ln of 3 times 3 to the 0. Now, officially, could you leave your answer like this? Sure. Would I like that you want to clean things up a little bit? Yes. So this is 5 over the natural log of 5 minus 5 to the 0 is 1. So minus 1 over the natural log of 5, which really, 5 minus 1, 4 over the natural log of 5. Minus. This, on the inside here, is really 3 over the natural log of 3 minus 3 to the 0 is 1. So minus 1 over the natural log of 3, which makes 2 over the natural log of 3. Could you find a common denominator, put all these together? Yes, you could. Is that really a lot of work? Yeah, are we going to do it? No, because I think this is about where AP would stop on a multiple choice. But again, on a free response, this is perfectly legit. Everything is a number, right? You've subbed in for all of your variables, so that number represents the area trapped between 0 and 1, between 5 to the x and 3 to the x on a graph. This last one is actually a throwback to a homework problem. I'm going to give you some hints to get started, and then you're going to pause and check. So if we're at f double prime, and I want to find f of x, my general concept here is that I'm going to have to integrate twice. What's helpful is that when I get to my first integration layer, I have a particular initial condition that will help me find the particular solution. So taking the antiderivative finds the family of functions, using the coordinate point 0, 1/2 will allow me to find what c was equal to. Then I'll get f prime, then I'll do the whole thing again, get to f of x, and then I have this initial condition that I need to meet, which will allow me to find the c there. So go ahead and pause your video and try this for yourself. Again, this is a previous homework problem, so you should have already seen it at least once. Pause now. All right, so here's all my work. Yikes. I came up with this thing boxed in green. So I took the antiderivative, used my initial condition. I got c equals 1. Did my antiderivative, used my initial condition. I got c is negative 1/4. Now, a couple of things to note. Getting from e to the 2x to 1/2 e to the 2x, I need to do a little u sub. Likewise here, another u sub. So make sure you're showing all of your steps. All right, that's it. The integral of b to the u, du, is 1 over the natural log of b times b to the u plus c.